All right, so last time we stopped around here. Uh, we have talked about the difference between sample variance and the population variance. Uh, a uh, very fundamental difference in which we know is that actually the design of sample variance is here, okay, and dividing this measure. This is actually not a measure for time. Okay, the minus one is actually represent concept of the degree of freedom. Um, so the population variance use the size of the population as their measurement. Also, you examine the degree of freedom for that population and that is, so the difference on the is according to the mean. That's your measurement variance. So um, okay, let's talk about something maybe further. You also need to really understand it very well. Okay, so the degree of freedom here, okay, I used to have the three number and one three five example. Okay, then you see that when you first take it a certain result, you have to say they have a certain result. Okay, um, that is regarding some fundamental design for statistical inference. Okay, actually, in the statistical definition, the for any kind of for any set of observation, no matter how you call it, observation or sample or whatever, okay, they are from a pool of numbers, okay, depending on your definition and restriction. Okay. So as long as they are from a certain range of numbers, okay. So if there are n numbers, n observations, you extract from the certain data range. Then for any one of observation, they are one random number draw from. So as long as you didn't observe this number, okay, this one number is a normal number, or homework is a random number. So if you have a population have an observation from a very possible range of data, each one of the observation is one random number. Okay. Before you really observe, before you really extract it from the whole, that's one thing. Okay. That's the so the case for small n here for the sample is that the cost for sample, usually by getting the sample, by the time you get a sample, although you usually don't go through all of the various time, you don't feel because all the numbers in the data is mean. Mean use all the numbers. So this mean value you get from the sample this actually apply a restriction to all the random numbers. So all the random numbers, all the random observations from the sample must have this mean. Okay, because you are already observed. So in your sample, your degree of freedom now reduced because you know one number. Okay, if later you know more numbers, that is calculated the uh, from all observations. Okay, you will reduce the rest respective degree of freedom. Okay, if in the future you take more advanced statistical class, information class, you will see that sometimes the degree of freedom will uh, it's not minus one, but minus a certain number of k. Well, mechanism that's not really, that's already very advanced. We already tried very advanced. So I don't really require to understand it right now. If at a minimum, we just remember it as it comes some of the rules. Once we talk about sample, use them. Okay. So with regard to set this stuff here, want to let you know this very early because this will be very useful later. Okay. In previous pages, we mentioned that the mean value here. Okay, the mean value here is actually a point estimate of population means, right? So also the S square here, we want to have this number because this number is a point estimate to the sigma square, to the variance of the population. Okay, and mathematically, if you follow the very old mathematician method of equation, only if there is one, unlike one here, this one is the correct estimation of sigma square. If you use n, this one will actually underestimate the sigma square. Okay, there are some mathematical background, but that's not really easy to know. No, right? Like you use your mobile phone, you don't need to know how the component in your mobile phone works, right? You don't need to know that much details. Just now we want you to be very clear for this, because later this one will be good estimation for the population variance, which is one country. Okay, following the content we have here for median variance, I will introduce median, IQR, other concepts. So they will very likely only appear now and will never appear later because still because of the estimation. Okay? Statistically, later we will learn one very important rule called the law of large number. That rule actually specifically say only the x bar can be a good estimator of mu, and only x square will be a good estimator of sigma square. Others, like the median, like the ordinary, others descriptive value that can describe the data, they have no statistical rules. They lose fancy and very often in our daily talk, we try to talk about data, we try to describe data, we tend to use our data set here. But for statistical inference, okay, for our ultimate task that we want to guess something regarding the population, only these two are usually used. Okay, that's why I want to spend some time here. Okay, but don't worry, okay, just conceptually have some impression of it, that's enough, okay, that's enough. As I said before, right, I take some courses related to statistics for at least 5 times before I got my PhD, right? So I really repeat it again and again so that I have those kind of sense, but for now, for you, we don't require you to know everything as well. Okay, so that's a ticket that as a simple impression going to be so clear. Okay, so a small conclusion here for some variance is right. It counts the negative positive derivation together as the same. Also, because of the square term, you weight the larger derivations more heavily. Okay, so that's a very small derivation for the variance. Okay, we use the so-called standard deviation, okay, which is just the square root of the variance. We have this definition, which does not create any new information because this one is sometimes easier to interpret. Okay, so the major difference between us and the mathematics is that mathematics don't care about interpretation. Okay, they just use as long as those notations are useful for those mathematics, they will use. They don't care whether they will create hundreds of different letters represent hundreds of different variables. They don't care about it. For us, we want to make sure that by the end, no matter what kind of conclusion we have, we want people to understand it as simple as we can. Okay, so here it comes to some disadvantage of variance data. So whether you use population or sample variance, the problem is that when you calculate the derivation, you take the square term. So the square term make it hard to interpret. Right. So like in this example, we use a hour of sleep per night as our observations. That as the variable we can observe. So to calculate the average average hour of sleep every night, it's very easy for us to see some number like 6, 7, 8, or more, right? That number is how many hours people sleep on average per night. Okay, it's very easy. You have a unit of measurement in hours, right? But what if we calculate the rights, right? We need to take the difference between hours and take the square term. So in terms of the unit of measurement, we are having some measure which is regarding hours square. This looks counterintuitive. It looks very strange to people's common sense, people's common understanding, right? So if we try to interpret the data by combining mean value and variance, it creates a problem that the mean value is easy to interpret. Okay, this is exactly just the average. But how can we explain a square value which have a very strict unit of measurements? Okay, so that's a very simple valuation here. Then we want to put it into a interpretable place so that we take a square term. Okay, try to take a square root term so that the x, the standard deviation, are at the end of the same unit of measurement as the mean value as all the other observations. Okay. So that's why it's sometimes you will see that people tend to show the data like, for example, hours of sleep, they tend to write it like 7 plus minus 2.03 hours. Okay, they show the data in this way by combining the values. So the 7 here is 0 is the average value, and then the value 4 in the 7 is the standard deviation that comes from here. Okay, that give people a sense that okay, by seeing this phrase, we know that okay, this means the data shows on average there are 7 hours people to sleep. Okay, and the variation is around 2.03 hours. Okay, so this is you see you now can combine the standard deviation with the mean value together, right? Show your purpose, right? Okay, so this is standard deviation where we give a very simple shape, okay, for interpretation. So yeah, median. I guess you learned this already. High school, it's very easy. Especially if you have all number of observations. This should be exactly one in middle. If you have a new number of observations, you need to take the two numbers in the middle, take the average of it. That's okay. Since the median just split your sample to two equally portions. So we also call it 50 is percentile. Okay, percentile means you split the sample into 100 pieces, right? Each you move from one piece to another piece, okay? You increase for 1%. So median is also 50 percentile. And we tend to have some measures regarding percentile if we sort the data from the lowest to the highest. So as far as median is 1/50th percentile, okay, we also have something similar, the 50th percentile and 70th percentile. As long as they believe that the data is minimum, is max. Okay, for example, 1, 2, 3, 4, 5, 6, 7, 8. Okay. Definitely this one is your median. They also will give 50% that, which should be fine. This should be your personnel. And you can see that it's actually just splitting the sample into 4 pieces. This is given the threshold between your first piece and second piece, right? So we also call the first quartile Q1 is 5. This is threshold in between your second and third pieces and your fourth pieces. And we also search quartile Q3. This will be. So we define, we additionally define a vector called IQR in the quartile range, which is the difference between these two. Okay, so with the median quartile things, okay, this is also an alternative way. Although by the end we will never use it later, but still they are very interpretable. Okay, and very straightforward. So we also have some way to show data regarding hotels and the median. This is a so-called box plot. The box plot shows the data vertically. So this is somehow similar to the dot plot. The dot plot shows the data horizontally. This one shows the data vertically. So in the box, okay, just the middle of the box, that's the median. Okay, that's the median. And the upper side of the box is your Q3, lower side of the box is your Q1. Okay, that represents the main body, the main body of the. Okay, so in addition to the IQR here, okay, which represent the main body, at least the main 50% of your data. Okay, they construct some concepts called whisker, okay, to expand it already. So we know that it has a full line, okay, upper and lower. So the whisker are defined as Q3 plus 1.5 IQR, Q1 minus 1.5 IQR. So that is because they try to use IQR as a benchmark and have a very just low habitual rule to argue that usually all the data will be in the 3 IQR range. Okay, so you have IQR 1 in the range here, right? If you pass another 1.5 IQR, you will reach your upper whisker, right? Minus or another 1.5 IQR, you will reach your lower IQR, sorry, lower whisker. Okay, so here one implicit assumption here is that people believe that as IQR, one IQR includes 50% of the data. Even if we try to use a very loose restriction to expand the range with the total 3 IQR, okay, maybe there are still some numbers out of the IQR. Then we try to argue that within the 3 IQR range, they have to be this normal, regular. If the data is outside of the 3 IQR range, we tend to argue that maybe that data is outlier. Okay. So the potential outlier defined beyond the defined as an observation beyond the upper circle. Okay, so case here. Okay, so once you draw the two whiskers, and this outside we just pack them as outliers. Okay, so we use the mathematical number of three many times in our average. Okay, we will see this in the. Okay, so we look for outliers for many reasons. Okay, and the most important reason is still coming back to mean and variance. Okay, so because the outliers, it sometimes represents some errors that we must correct, right? We will have some students GPA data is larger than 4.0, that might be an error, that's a mistake with our data. So that's definitely possibly avoid. Also, in some cases, like depending on the research question you have, you don't want some extreme value to affect your interpretation or affect your judgment. Okay. For example, if you are some government office, you want to design some policy regarding people's like for example students rental fees, right? Like how much students should spend for their dormitory every year. Okay, so in that case, you may survey all the students here and there different university schools. And sometimes there are some students they don't live in the school, they live in their own house. Maybe but perhaps the parents are billionaires, so the parents justify very luxury house near the campus and there. Okay. So in that case, they can either report a zero rental fee or sometimes they just report the average expected rental fee for their now currently own house. That will be very extreme, much higher. So in that case, if your research question or your purpose is to design some policy for all the people, all the students, okay, counting these kind of outliers will not beneficial at all. They will only bias your data. So in that case, you must have some ways. Whether you just exclude this data, you drop this data, you don't count it, or you well measure it in some way. Right. And also, I want to get back to the first bullet point here is that outliers will help us identify the extreme skewness in the distribution. Okay. So for example, here, this distribution, as long as the outliers are there on the right hand side, far right hand side, okay, makes the distribution be right skewed. Okay? So the skewness is actually a thing that we must take care of very carefully. Why? So still to come back to the argument here. By the end, later, you will always use the x bar and x squared, mean the variances framework to do your statistical inference. And unfortunately, this tool will be affected by extreme values very much. Okay. So you see, we just use this annual household income case as an example. We know that most of people have their income within a certain range. There are a few, very few billionaires out there. Okay, so you can see that for the original data, median IQR of this number. Okay, you can also calculate the x bar and the s. Okay, looks okay. And if you move the largest to the median is the 1e plus 0, 1e plus 7. Okay, so it's 10 times the current value. If you move one largest value to 10 million, Okay, the median and the IQR will change as the sequence of all the data are still the same. And you just change the largest, make the largest even larger. Still the median will remain the same. IQR also the Q1, Q3 will remain the same. This will looks okay. But your X bar and S will change a lot, right? Your standard deviation changes so much, you increase for 4 times. Okay, and your X bar also increase for significant level, right? From 225K to 300. And if you make some other switch, like you don't change the largest side, you change the lowest side, move one number from the smallest to the median. Okay, you slightly change the sequence of data, then your median also change a little bit, but that's not much, right? 190 or 200, not change much. Like you are remains the same, then your X bar increase even more. Your standard deviation is also very high. Okay, so you can see that unfortunately, although you right now you know it that eventually we will use this median or framework to do our statistical inference. The problem is that they will be very likely affected by the value. That's why by the end, this is the most fundamental way. Although it's indirect, we have to understand in other ways. This is actually the very fundamental way that why we want bias. Okay. So in addition to outliers, the skewness itself also have some problems with the framework. So now we can conclude that for skewed distributions that we have before here, maybe use median and IQR to describe them will be more proper. And for the symmetric case, mean and standard deviation is more proper. But the problem here is first still we will by the end end up with mean and framework. Okay, so if the skewed distribution is hard to be described by this framework, we must have some way to make it symmetric, to make it as close as we do to a symmetric distribution. Okay, so that we can get back to our comfort zone, can get back to something we are familiar with, we can do our statistical interface. So one is very, I would say, not really important information I want to have here is that although the ability of statistical inference is some kind of limited, as you can see, okay, we cannot use median or the IQR to do statistical inference data. We can only use them to describe now. But the others, they looks limited, but they are self-convinced at least. Okay, so for example, you see that it's actually necessary to have a symmetric distribution, not only because by the end you want to use as square, but also because if the distribution is symmetric, for example, let's use just this distribution. If this distribution, according to the middle line, is very symmetric, they have a very nice feature, which is that some measures for centrality are the same. So in our introduction, we have a mean, right? So if they are symmetric, it's very natural to expect the mean value is just at the top point. Also, if they are symmetric, that means on the left-hand side, right-hand side, just 50% data are here, and another 50% data are here. Then the median point should also be this top point, right? So mean also median. Okay, and although not in our slide, but at least in your high school, I guess you learned something called mode, right? Which represent the most frequently appear number. And for symmetric distribution, as long as they are symmetric, the mode will also very likely appear here. Okay, unless you have some distribution like this, okay, then the mode will be here or here. But usually this will not appear in the real world. Usually the real world have some such central tendency, so data tend to get crowded into the center somewhere. Okay, so with this symmetric distribution, your model is also the same as the previous way. So in this case, that means with a symmetric distribution or a close to symmetric distribution, all these things are actually the same. Okay, so whatever you want to refer to, okay, as long as they are the same, it saves a lot of your energy. Right. But if you come to a skewed distribution, the story will be different. For example, if just still for simplicity, you plot the distribution like this. This is a right skewed distribution. Okay, let's see that maybe most of the data will be around 1 to 100. Okay, and there is there is one data point. Oh, so two data point here equals to 10 million. So as long as this number is very large, it will drag your mean value to the right hand side. Right? So your mean value, if you try to display it in the distribution, might appear here. This might be your mean value. Okay, because this number is large and count for all xi divided by n. This mean value will be large, right? Then, if you think about the median, for the median is just at the 50% of percentile, and it should be less affected, right? Just as we said before, median IQR, it should be less affected by the skewness. That means although the mean value is on the very far right hand side, the median should be still around the majority of data, right? So the median may be around here. Still, if this case is very extreme, like all other numbers, like 99 ohms are here, only one observations are here. Okay, only this one observation change everything. Okay. In this case, if you think about the mode or the most frequently appear number, okay, so this will very likely be even lower than the median here, okay, at least in the here. Also, this two may not always true. Okay, this two sometimes mode is larger, sometimes the median is larger. Okay, this two not, but at least you know that this two will remain. But not at least you know that mean should be larger than median. Okay, these two numbers are different. So here this is actually kind of another explanation for us to take care of outliers, also the skewness of data. Okay, because if the data is as good as close to the symmetric, it saves a lot of energy, right? You talk about mean, at the same time you also talk about median, or even the mode. But when the distribution is very skewed, and you need to separately talk about different statistical measures because they should take different values, right? So so some action you can do, like one action you can do to get those skewed distribution back to something you are output of this is the log transformation. Okay, so log transformation is basically trying to take the logarithm value of each observation in your data. So if your sample, when the size is x1, x3, or so on, you just transform into log x1, log x2, log so on. Okay, although there should be one assumption that if only your xi larger than 0, right? Because I guess you still remember what is logarithm function, right? Logarithm function is this. So it only takes larger than one and no less than 0 value, right? So if the xi is 0, the log xi will be negatively defined, right? And we take the logarithm transformation because the log function have a good feature, which is they have a concave shape here. What I mean here is that for the same increase in x, okay, if you increase x for maybe like 100 here, okay, the corresponding increase of y will be like this range. And if you extend it to the far right hand side, maybe here, okay, you increase to the same 100 plus the change for y will be smaller than here. Okay, so it's or in very mathematical way. It's a second derivation. Okay. So with this feature, it can actually very effectively control outliers. Right? If this is 10 million, so compared to 100, 10 million increase a lot. But as long as the log function looks like in this shape, once you take the log value of this 10 million, it's not that much. Okay, so we use this example here. Okay, this is a number of possible games attended by students. Well, it's a game that not everyone like, right? So the majority of people, they have their own habits. Right? They go to play football, they go to play the rugby, others say chess, whatever they want. So very likely, most of people stay with the first bar, right? The first bar is histogram. Okay, you know that some of the people they are passionate about basketball. They play it for 50 times, 70 times a semester. That seems so easy for them, and even not enough. So if you draw the distribution for number of basketball games attended, okay, depending on their interest on this game, it will show a very well right skewed distribution. And then for you, if you want to do any kind of statistical inference, this will be a problem, right? Because you see, because the x bar and x squared will be affected very heavily. So instead, we take the logarithm of all the value. So we can draw the distribution like this. Okay, and here for simplicity, they actually try to add some value here, like for log here, they add 10 here. Okay, I just want to make sure that the distribution starts from 0. But whether you add 10 or not, this doesn't matter at all. Okay, so you can see after you take this function, you take the log transformation. This one still a bit right skewed, okay, but it's much better than the left side. Okay, it's now have some kind of tendency looks like symmetry. Okay? So this is one way to deal with the rescue data. So sometimes when we do the statistical inference, you may see that they first take a log transformation for or they want to investigate, and then they run those statistical techniques. Okay. By the end, turns back to the very root of the theory, because this tool will affect the experience. Okay, that's why we take care of it. Okay. So, for example, the research on salary, on housing prices, etc. So they were very likely before we run any kind of statistical first they will do not. That's a very small piece of transformation. If you do this transformation, it's a bit hard to interpret. Okay, still we come back to why we have the derivation, right? You have the derivation because long interpret data to the general public. So anyone even without any even without any knowledge of statistics. But here, if you have some log transformation here, right? So you will transfer the data, log number of pages like over 25, 391, it's hard to explain. Right? The person played 70 times of this game. That's easy. I don't understand. The person's log number of games played is over 25. People are confused. That's a very small kind of problem. Well, that's not even a problem in finance. I'm a finance that's a legal finance. Because in finance, there is some trick with logarithm function relation. Make sure that the even logarithm return can be explained and easy. Okay, so in finance this may not be a problem, but usually in real estate, in other cases, okay, this logarithm transformation will be very hard to explain. Okay, so yeah, to conclude this part, I want to use this intensity map to kind of conclude to establish the importance of graphical display. Okay, this pattern, this map actually shows a change in population within 2000 and 2010, after 10 years, after a decade, how the population in the United States changed. Okay, in terms of each county, each city. So they use blue color to represent the increase, yellow or green, orange color represent of decrease. We can see that really this reflects the common study and say that one picture is more than 1,000 words, right? If you write down all the data for each county, it will be a very dense table. Okay, and looking the county's position on the people are in 2000, other people are in this county by 2010. And now, if you put all the data into this map, you can see that it's the benefits are very straightforward. You can exactly observe the increase and decrease of people in the United States. Easy, right? You see that usually in the east and west coast, population keep increasing, but in the middle of sometimes we call middle of nowhere, right? In the middle of the United States, population keep decreasing. Right? It's quite natural because if you check the geographical status of the United States, actually in the middle of the United States, there's no rain at all. Okay, so they always suffers from the scarcity of the food and the water supply. Okay, but on the eastern coast and western coast, the nature is much better. Okay, so so the next part here is the so-called display is categorical variable, but I won't spend much time here because you already know these things in the previous slide, right? These things, and now I just let you know the formal name of those tables, like this table, split your results depending on different features and outcomes. This is called contingency flow. Okay, so For example, this one is the one regarding the mechanic. Okay, let's see how many adults die, how many adults survive, how many children die, how many children survive. Okay, so those numbers can be drawn in the bar plots. So this one is a bit different from histogram. Also, the rules are also the same. The main difference is that the bar plot is used for categorical programming. So under each bar, there are categories. They have no connection. For histogram, under each bar, there are certain data range. So the data range are connected. So you see, histogram is actually a continuous. Okay. Also, because they are categorical, you switch sectors, a lot of it's not possible for histograms. Okay, so some similar way we have done before, okay, we can calculate the ratio of survival for adult and children, see if a certain age group survive better. So for these two ratios, we can have some way to show it. I use some variation for bar plots. Okay, there are three variations. Okay, we show them together. So this one is a stack. Okay, so instead of show the adult and show children in two different figures, we can show them together. Either stack them together or put them side by side here. Okay, by the way, if you want to show the difference in survival percentage, like we just calculated in the previous slide, you can use the relative frequency here. Okay, you change, I'm going to change the definition for y-axis. Okay, so here is the survival percentage. Here is the percentage because of survival percentage. Okay, and you see with this figure, you actually make some kind of argument, like what you have here with the ratios. Okay, and also if it's improved version, you can use the same like the model plots. Okay, that's use the adjust the variation of this standardized expected plots. Okay, so this one is actually the almost the best one you ever have because now I change the result data, also shows the number of survival level of that together. Sometimes it needs some knowledge for you to understand more than plots. So that here always some trade-off, right? If you want the bigger, you do the all the necessary data you want. We sometimes require the audience to have some knowledge to understand each. Okay, I try. If you have too many categories, or in part. So this example is jump. Now we just jump to gender discrimination study. Okay, I think this one is actually one very interesting one. Actually, we will use this to introduce some very important concept called hypothesis testing. Okay, well, just for the research itself, I feel it's very yeah, since I also made some research regarding distribution, so I could tell this one is well nicely designed one. Okay, so I think those discrimination or inequality stuff are more important in recent years. Okay, whether like it or not. Okay, so not only about gender, but about race, about a certain group, a certain unequally treated group. But what we observe in the society is that although those processes are very sounding, people always use it in the wrong place. Okay, so let's use this study as an example to see how to really argue a discrimination problem was effective. Okay, so they study the gender discrimination. They select 48 male bank supervisors. Okay, let them deal with exactly 48 profiles. Okay, they let them get the same personnel profile, ask them to judge whether this person should be promoted. So the profile is just like a one page or several page resume. Okay, to include the person's achievement, their working experience. Sometimes, and very likely they hide the name, okay, to make sure that the name does not show any specific information. And sometimes a specific name will show the race of the person. And sometimes even the name can show the age of the person. Okay, because for a certain decade, right, people tend to very frequently use a certain name for the children. Okay, so in this kind of research, they usually tend to hide the name. So the profile is designed to be identical. It's the same as each other. And only the gender column is different. So here, I think the design is very, very nicely controlled because usually a very common mistake for people who do some research about discrimination. They really let people comes out and interact with the interviewer to do some research. Okay, but once you lose how the interaction, it actually make the research uh, less valid because there are many sources of information once you meet the people. Okay, so if I meet the people, if I meet myself, I will say, okay, this guy is an Asian guy. Okay, about what kind of years old. Okay, we're wearing glass. That means he's Ivy League, really that good. Okay, we're some clothes, like decent figures. Okay, we're what kind of watch. Okay, so you can observe a lot of soft information by just have some simple interaction with the person. In that case, you really, at the end, whatever things you observe, you cannot conclude that your result is based on a certain type of discrimination. It's hard. Right? Maybe the discrimination is based on the person's race. Maybe the discrimination is based on the person's faith, right? So by just sending the resume to the supervisor, you control almost everything. You control the other variables effectively. So this one, if let me draw this one is more like an experiment, okay, because you do fact how the data generated. Okay. So we use the continuous table here to draw the results. So it seems like the well managers are promoted more likely. Okay. But still, by now we don't know. By now we still don't know. Actually, as I mentioned before, okay, if you flip the point 100 times for real in our real world, okay, it's very likely you cannot get the exactly 50 times half. You will get 51, 52, or 47, 48. Okay, in the real world, we have learned this. Now we can only get the number, but we cannot have any successful conclusion to say whether these two are meaningfully different, whether these two really reflect any discrimination. Okay, although it looks like have something, okay, but as a college student, as you learn science, okay, you cannot just draw a conclusion by emotion. Okay, so some kind of question we can ask, uh, the, the table we have, and this will always our conclusions. Maybe we can conclude. So, but the most important thing I want to introduce here is that I want to introduce the hypothesis testing framework regarding the case study here. Okay, so when we try to think about whether those data reflect the gender discrimination or not, we are actually asking the question under the hypothesis testing framework, which is we are trying to create a two counter hypothesis. So the one hypothesis is the null hypothesis. We say no, they we want to argue with is that there are something running, and there are some relationship between the gender discrimination and the promotion. The gender discrimination at the cost of promotion, maybe. Okay, that's the single want to argue. That's the one you want to provide the data to show. Okay. So this logic is basically like a control. Okay. So always, if you do not start the control, the defendant will be just there, living happily. Okay, even if actually that defendant may commit a very highly severe crime, right? As long as you don't start its control, everyone will live happily, really there. So what we want to do in the court is to provide enough evidence to show that that person is really guilty. So it's unlikely that all the data you draw is just based on chance. It should be that because the person is guilty, so that the data show that pattern. Okay, so that's why we asked here how unlikely is unlikely. So that's exactly what I said before. This is the most important question of fundamental class we want to have for statistical inference is that we want to know how good is the probability that. Okay, so here are some characteristics with the phrasing. Okay, so the null hypothesis we tend to talk is the so-called status quo. Okay, means that's what thing is originally there. Okay, we call it the status quo, we call it null hypothesis. And our argument is regarding alternative hypothesis. Okay, and our proof, the concept of our proof, is to get more and more data, get enough data, very unremarkable, to show that the alternative hypothesis is more possible. Okay, but for conservatives, okay, ours for research, you need to be conservative, you need to be precise. So we never say if we cannot find enough evidence, we never say we accept the null hypothesis, or generally we never say we accept anything. Okay, so if you always can easily say I accept this, I accept that, now there will be some problem. Yeah, this is because you accept too many things, right? It makes your knowledge set too complicated to accept too many things. So conservatively, we never say we accept anything, we never say we accept null hypothesis. Rather, we say if we do not have enough evidence, we say we cannot reject the null hypothesis. Okay, we do not have enough evidence to reject. Okay, this is a very precise logic chain. And if we have enough data, okay, still there is a logical reason. Okay, there is no perfect data. There is no perfect events to observe. So we cannot perfectly reject the null hypothesis and accept the alternative hypothesis. And we cannot be 100% sure. So usually we only say we reject the null hypothesis in some level, in some way, but we never say we accept the alternative. So we never say accept. Okay, to draw the conclusion with hypothesis testing, we always have two choices only: to reject the null or to not reject the null. Okay, so that's just to make your argument logically precise. Okay, so that's not your childhood, right? It's not that okay. What kind of person you want to be? I want to be a scientist. Okay, like that. That's good for children, but for adults or college students, we need to be very precise for all arguments. Okay. So I think this one let me recall some skills I used to have when I was a high school student. So when I was in high school, I was so confused with those experiment reports like in biology and physics. So I was so confused because I don't know why. After I write down the research question, I need to write down another two lines to say that okay, we have a hypothesis that maybe A and B can react, but we also have the null hypothesis that A and B do not interact with each other. So after I come to the college and learn the statistics, I know that actually after the research question, you write down the counter hypothesis is meaningful because that is uh, that is an implicit declaration. It declares that you are about to use the hypothesis testing framework to make your argument. You are about to provide data to see whether the data evidence is significantly uh, supporting your argument, supporting your alternative hypothesis. Okay, so you state those hypotheses there. There are some meaning. Okay, it's like you try to you basically announce that okay now I will use a certain method, use a certain framework to make our analysis. Okay. So generally, what we want to do is we want to use data to exclude, or at least largely exclude that is all the variations, the difference between the male promotion rate and the female promotion rate is due to chance. So we want to exclude this possibility. Okay. So later we will have some ways to make a calculation, but now I just want to understand this based on one example. Okay, so luckily because the case we only have 48 cases, 48 promotions, so we can use the cars to make a simulation. Okay, so if we have some cars like this, okay, we use GQK, the face of the car. Okay, we use GQK as uh, GQK plus 1/8. Okay, in total 13 face cars. Okay, we use them to represent the promotion. Okay, and other non-face cars, those number cars, okay, we use them as non-promotion case. Okay, so in total, we just make sure that you have 35 number cards, you have 13 face cards, so in total you have 48. Okay, that is exactly the number of promotion cases you want to have in the discrimination study. Okay, so for simulation, what we can do is to split these 48 cases by shuffling the cards, okay, and just put them into two groups with equal group size. Okay, and then we review the result. We see that okay, in the group on the left hand side, okay, how many face cards we have. Okay, in the group on my right hand side, how many face cards we have. Okay, so we can calculate the ratio of promotion, assuming this is the male group, assuming this is the female group. Actually, whether this is not, it doesn't matter, right? Just what the interest is, second difference. So this is just a one time. This is just one way for you to simulate it using card. You can do this simulation by shuffling the card many times, and with the same set of cards. So if you shuffle the data for enough times, maybe by your hand, maybe use some software, okay, and you can note the difference in promotion rates. Note this second difference result here. Okay. At the end, you will observe some result like this. Okay. Coming back to the example. So what you observe by the end is 0.875 versus 0.875. So this should be 0.292, right? About 0.3. So coming back to the conclusion of this simulation, you see if you want to find some place for this, it will be placed around here. Okay, so if you simulate for enough times, and the actual result you observe from the real world is on this scale, far away from the majority, you may conclude that, okay, considering that what you observe in the real world, the difference is as large as around 0.3, which is sufficiently larger, which is sufficiently large comparing to the other simulation result, we may conclude that it is very, very likely that we can reject the null hypothesis. We can say that there is some gender discrimination in the promotion. Okay? So this is actually the common case. This is actually the common case. So now here, the simulation, in many cases, the simulation is still the most effective, the most fundamental way for us to compare the actual data with the expected data. If there is any very extreme difference, you would say there should be some evidence that let us reject the null. Okay, so what we will learn in the later chapter is that we will add more assumptions to this simulation. So instead of using simulation, we'll assume that the simulation results, we assume the simulation result will follow some kind of distribution. Then by having those assumptions, we don't need to spend our time with softwares, with struggling the code. We can just use some very simple formula to draw the same conclusion to reject the null hypothesis. All right. So that's the main part, almost everything. So basically two important parts. The first is the logic here. Okay. Why we talk about median IQR, but by the end we want to correct for outliers series. This. That's one thing. The other thing is the hypothesis testing framework. Okay. Make sure you understand this stuff. Okay, so that's all for today. Any questions? No. Okay. So yeah, this week we don't have lab yet. Okay, but next week we have. Okay, so now you are free. Okay. Enjoy your afternoon. Enjoy your lunch. Enjoy your dinner. Okay.